All right, can everyone see it's recording on your end? Good, all right.
Yes.
Thank you very much for being here. My name is Michael Halvorson, Chief Engineer for the Alabama CubeSat Initiative. Today, we're going to talk about systems engineering. We are going to go through about a semester's worth of advanced systems engineering material about as fast as we can. Please ask questions at any time. Anytime you got questions, ask them. I'll be around at the end of this to answer any questions that you might have. But we're going to try and jump through as much material as possible. And thank you all for being here and taking the time to commit this material to memory, hopefully. So let's get started. We're going to start by saying who a systems engineer is and what that person does. We're going to move through the life cycle that a systems engineer operates in, the stakeholders that care about the material you're working with, the concept of operation, the operational concept, very dumb that they're named that, requirements, the hardest part of systems engineering, which is integration, talking about V&V, verification and validation, technology assessment. So what's your technology readiness level and how do you determine that? Technical performance measurement, which is another very difficult part of systems engineering to do correctly. What are risks? How do we describe them? And we'll summarize everything to really hammer the points home. Okay, so who is a systems engineer? When we're dealing with systems that are complex in that they have lots of interfaces and complicated in that they have a lot of inputs and outputs, you need to understand those systems from this top-down interdisciplinary approach. It's not all going to be electrical or software or mechanical. You got to have everybody involved in the conversation. And a systems engineer will perform certain tasks at the beginning of a life cycle, so the concept and development phase, versus what they'll do at the end, the operations and maintenance or the retirement phases. So systems engineers oftentimes don't have the clear problem statement in front of them. All they know is stakeholder needs or what people want out of them. So if we were talking at the beginning of the early 1900s, if you'd asked people what they wanted, they would have told you faster horses. Well, how do you get from faster horses to I want a car? You got to define the problem and then solve it. And that is what's important to us and what's important to us right now. So this is the formal definition, a lot of text here. We're going to step through this. It's a multidiscipline application, analytical, mathematical, scientific, maturing an optimal solution from a set of viable candidates. That's really important. Has acceptable risks, satisfies those operational needs, and all of this has happened while balancing the stakeholder interests. Your stakeholders are going to want different things, possibly conflicting things. At the bottom right there, you see the Ouroboros, the dragon ate its own tail. This is often a symbol used to describe systems engineering because it's not a linear process and it's not supposed to be. So there are 6 general sections in a systems engineering process, and it starts with concept and then developing that concept. Then you go into a production phase. Some systems do. Software, for example, doesn't have a production phase per se. Then you go to utilization, support, and finally you retire that system. But iteration and recursion is possible in all paths. So even when you are, say, testing or integrating a system, that might influence what your requirements are earlier in the development process. So it's not that you just nail your requirements and move on. It's not a linear process and it's not supposed to be, but understanding what you're supposed to do at different life cycle phases helps you understand this material. So a lot of material on here, but it's important to know where we come from. So a lot of you in your work produce documents, but that's not what systems engineering is about. Systems engineering is about decision making. It's about understanding the purpose of the documents and then executing along the procedures defined in them. So in grade school, what we learned at the very beginning was the scientific method, where you have that hypothesis and you design an experiment and you test the hypothesis, you get your conclusions, and then you communicate those. Okay, scientific method. And then you go into your undergrad specifically senior design, and there's going to be some problem given to you, or you'll pick it, and then you'll do some research and you'll create requirements and then communicate those in a PDR or something. You'll look at alternatives for the design solution, and you'll pick one, and then you'll go build a prototype and then test and retest that prototype as necessary. And then you'll communicate those results in a final report. So that procedure is called specify, design, build, test, fix. Specify, design, build, test, fix. And that right there is the problem. It's the fix part that will end up costing you time and money. So when we shift from the SDBTF, specify, design, build, test, fix mentality, what we're going to shift to is understanding what the problem space is, not just a single problem statement. You do get there eventually, but what is the full space surrounding that problem, and how do we look at it from different perspectives, mechanical, electrical, software? And then we define an opportunity space around that problem space. What is the opportunity that exists along those different views, mechanical, electrical, software, what have you? Then you look at your domain solutions from the variety of views you have, and those domains are always going to include requirements, operations, behavioral, and physical. Those domains always exist. You get the architecture, which is what, and then you translate the architecture into design, which is how. You do the assembly and integration, you implement or realize that integrated system, then you have operations and maintenance or support sometimes, and then you retire that system. So that is how we are getting from the scientific method to specify, design, build, test, fix to the professional systems engineering understanding of the opportunity and problem spaces that exist, ultimately transitioning into the solution space. So that specify, design, build, test, fix is the exact method taught in most senior design classes. You get the problem, you find a solution, you build the solution, you test the solution, wipe your hands, go graduate, do whatever, make $1 billion. Great. But that doesn't help you or your company. It's a bad way to do business. And then if you don't learn any differently, you just take that on into industry where we continue to lose time and money. It's an endless loop. And the problem is that there's no real outcomes understood when you start the procedure, other than I need to design, I need to integrate, I have to deliver on time and budget. And it doesn't have a lot of regard for what the user needs out of the system. So yes, you might have created something that fits the user needs, but it might not be validated to be exactly what they need compared to something else you could have delivered them, which is a reduction in ultimate value. So we are maximizing value here by understanding the process that we're going to use to do or execute engineering. So when we talk about a system, in system engineering, we need to understand what a system is, and that system has elements: products, processes, people, information, techniques, facilities, services, support. Yay. Those are just ways that you can define it. There's many ways to do it, but you need to understand what elements do and do not exist in your system, and then associate those elements with domains. So what are the requirements for my processes? What are the people involved in the behavior? What are the physical techniques that I'm integrating the system in? So you kind of have a matrix of your elements and your domains, and there are architecture frameworks that'll do that, but you can create domains and elements as you need them for your system. And then after you define that for your system, you move across that matrix, understand it, and that is how you're going to elevate your engineering process. It's not, you have to have the full systems thinking. So when we're talking about systems thinking, this list on the left, from purpose, problems, assumptions, views, data, concept, conclusion, implications, that's a good flow to take. If you can take that flow and then relate the domains to the elements, you will encapsulate a system using systems thinking. It's important when you're doing this to start with the output and work backwards. Starting with input can lead you kind of in a Monte Carlo simulation to a variety of different solutions. Start with your desired output. Whatever is validated for your customer, for your user, what is it that they want? Work backwards to understand the inputs from a variety of views for your elements, and then you can translate that information into your system architecture, the what, and the system design, the how. So, not a linear process, not supposed to be. Understanding all of this, we know that every engineer is a systems engineer. There is not a single one of you in the command and data handling or flight software or mechanical structural integrity teams. Every single one of you is using this information in your day-to-day activities, which is why every engineer is a systems engineer. When we're talking about large-scale industrial systems engineering, there is an optimal amount that you should spend on that. David Honor is an Australian guy. He interviewed a bunch of executives and figured out optimally how much they were putting in on this. 14.4%, and it's a little bit higher for space infrastructure. So if you're spending $10 million on a project, $1.4 million of that should be on systems engineering itself. Any more or less than that, you're either going to spend too much to gold plate your system, or you're going to have to fix it later. And that's the specify, design, build, test, fix that you learn in senior design, usually without fail. Not every time. Okay. Any questions there? Who a systems engineer is, what they do, what is a system, how do we characterize systems? I'll stop at all of these intersections to ask questions. If we're good, we'll move on. Okay, so understanding your life cycle means you need to understand your domain, because they're not going to be the same life cycles for every domain, and there's not just one correct life cycle for any kind of domain. You do have to define the domain, and there may be multiple life cycles within that domain. So on the right here, you can see an example of domains from Blanchard and Fabricki, but this is a bit of a better relation of domains to life cycles. So in, say, we said earlier that software does not have a production phase. So a general system is this: concept, development, production, utilization, support, retirement. That's kind of as vanilla as it gets. But then you start to tailor it for your system, which is something you do have to do. So in software, you'll have the concept and then the development, and then you just deploy it, and most of it is deployed really quickly, because if you're not embarrassed of your MVP, then you've launched too late, and you start performing patches, operations, and maintenance. Yay. So the point here, figure out what your domain is, figure out what life cycles work best for you, and tailor your systems engineering processes to that domain. What the best thing to do is it works for you within reason. Don't just throw the systems engineering baby out with the bathwater. Understand what it is that you're trying to do. So these are some examples of life cycles that exist. DoD 5000, that's the one that the Department of Defense uses. NASA 7123.1C, that is where they define their systems engineering principles, and we'll see an example of that in the next slide. IEEE has one, ISO, IEC has another. One that I think Wasson does a really nice job with this, but it is cradle to grave service, as they call it. And if you're trying to define your life cycle for your systems, this is a good place to start. This is a good place to understand it. Obviously, these slides will be made available through the Alabama CubeSat Initiative website. Okay, so this is that the NASA single project life cycle. Yes, or single mission project lifecycle from NPR 7123.1C. So what you're looking at here are reviews. You can see in the middle, you have system requirements review, mission definition review, system definition review. You have a PDR, preliminary design review. Many of you have probably heard of that one. CDR, system integration review, blah, blah, blah. Here's the acronyms for those. These are called stage gate reviews. That's the formal name for it. some people call them milestone reviews, but again, freedom units are formally defined as metric units times a conversion factor. They are wholly worthless and should be forgotten. So we don't use the term mile whenever possible. There's 4 results that you can get in any stage gate review, and that's go, hold, recycle, and kill. Go, obviously you proceed, you are good to go to the next review. Hold, you need to stop and wait probably for someone else to finish something before you can continue. Recycle, do it again, not good enough. Kill, we don't think there's value in continuing this, and that happens quite a bit whenever people need to revector resources. So out of those, what do y'all think is the worst? Go, hold, recycle, or kill? Somebody give me something.
Is it hold?
It is hold. If it's hold, it's a really good time to go on vacation. You have no idea when it's going to pick back up. So excellent. Bonus points to you. You get an A and can drop out of college. Okay, so that's your life cycle. Any questions? All right. So let's talk about who stakeholders are, why we care. These are generally, well, not all of them, but these are people with money or power. These are going to be the people who are going to influence what you do and why you do it. NASA, there's internal versus external. NASA calls internal stakeholders participants via NASA standard 1005. All of you in the Alabama CubeSat initiative who are working on some subsystem, y'all are internal stakeholders, users, operators, developers. External stakeholders are going to be people outside of the program who have some say in the results. If we are doing a science mission, astrophysics, heliophysics, earth science, a science mission directorate, NASA has many, they would count. The FCC, regulatory agency, that they count. The communities that we would publish the data to, they are stakeholders, and they have a legitimate interest in these systems. So they're not all the same. Obviously, these stakeholders, the FCC is not going to have the same concerns as the scientific communities. If someone has invested in you, they might require you to give a quarterly report. So that influences the things that you have to do. The page number messed up. I hate that. So anybody that you're interacting with is also a stakeholder. So if you're contracting out a service, they would also be a stakeholder here. Below, you can see some examples, for ABEX or astrophysics payload. That's the astrophysics science community. For space taxi, our qualified hosted platform. These are anybody that is going to pay us to take their payload into space. They are stakeholders. We are beholden to them because they have paid for something and we have to provide the good and service. Yay. Stakeholder needs are often represented as I want statements. I want this out of the system, or I want that. If a stakeholder says, I want a car seat to be warm, we'll talk about this in the voice of the user later, the requirement might be translated into the car seat shall emit 10 watts of heat at minimum. There's a better example later, but that is in general the idea. They are going to say I want, and then we have to decompose that want. But again, some stakeholders are dumb. Some of them don't know what they want. If you'd asked people at the early 1900s what they wanted, they would have told you faster horses. One of the most famous planes of all time was the DC-3, and that was originally a statement of work for a wood plane. So they were going to make it out of wood, and they ended up making it out of metal, and it was a totally different version of success. So yay. When you know your stakeholders, you can understand your life cycle, and then we'll move into the concept of operations and the operational concept. Any questions on stakeholders, who they are, what they want, why we care? All right. moving on along. So ConOps and OpsCon are not the same thing, and that's dumb. There is a AIAA standard that they say the quiet part out loud, where it says this confuses people because it's the same name, but they're not going to change it, which you kind of just need to accept at this point. But it's okay, because you just need to understand what they are, and then you can communicate their contents in a variety of ways. Like, we don't have an OpsCon and ConOps document, but we still do the things that they want in a variety of ways. So let's get into that. We need to start drawing a line in our head when thinking of a system of what versus how. So architecture is what, and design is how. And that's a good way to think about the OpsCon and ConOps. That OpsCon, the operational concepts, is what and why. So this is relating an architecture to stakeholder needs to make sure that an architecture is validated, it's the right thing for the stakeholder needs. The concept of operations talks about the actual operations of what the architecture is doing and how that translates into the design. So that is how and to what end do we care? All right. So the voice that you speak in matters greatly. There's a difference between the voice of the user, so whoever is actually using the system you're developing, and the voice of the customer who is asking you to make the system. I think an aircraft might be the easiest example here. The users of the aircraft are either the pilot or the passengers, and the people who buy the planes and use them are not, they don't have the same stakeholder needs. So here is that car seat example. If a customer tells you, I want to be comfortable, then the requirement translation is the car seat heater shall provide a minimum of 10 watts to occupant. Yay. That OpsCon, the what and the why, that's voice of the user. What are we doing? How do we describe the system? What and why? The concept of operations, how and to what end, that is a very formal thing. We are describing operations systematically. That concept of operations is really where we're going to apply that matrix of domains versus elements and translate that design architecture into a design. Cool. This is more about the operational concepts. It's easier to write an OpsCon before a ConOps, which may seem obvious, but it should be stated because not everybody does it. Write what before you write how. This needs to be stated in particular because we said earlier that you need to start with what the system does and work backwards. Start with what the system does and work backwards to architecture, and then move forward into design. It's not a linear process, and it's not supposed to be. So the ConOps can be this big, long document, and we don't want to give y'all something that is this big, long document because you won't read it. So you need to decompose what it is that the intent of these documents is and how that's being translated into the actual content of the document itself. ConOps assumptions or intent, and then specific operations. This is the rigorous engineering voice. But again, the goal here is not to produce documents, it is to make decisions. All right. The ConOps is often something that, whether you know it or not, when you first get into your senior design or really any engineering project, you're tempted to jump right into it. And there is this problematic theme that always shows up, or not always, but very, very consistently, is this is my problem, this is my solution, this is why my solution is good. So you're given your problem, you do an analysis of alternatives, you do a trade study, figure out what your best solutions are, and then you put those together and then express why your version is best. You're gonna have to fix it later if you do it that way. That's, I can't express that enough. That linear process is going to result in needing to fix it later because, one, it doesn't work, or two, because it God, a variety of reasons. It cost too much. You took too long. It's not. This is not the right way to go. What you should do is go analyze your problem space, look at it from the views, the elements, the domains. What are the requirements for the physical nature? What are the operations that I'm going to have to do for the people in my system? Understand that problem space, and then define an architecture that meets that problem space, and then assess how that architecture could be decomposed from what into how, and that comprises your solution space. That's the variety that you're looking for when we're saying don't describe one solution, describe all of them, and it's more complicated than just doing a trade study. Then you compare the solution space, how each of the design options meets the conjunction of the domains to the elements, and then you write up a comparison of how the solution space meets the problem space, and then boom, that's how you could define your ops or ConOps. Again, we are not going to do a big long document because you won't read it. So what we're going to do, or what we have done, is we've decomposed the elements that exist within the ConOps and the OpsCon into a variety of documents. It starts with the project summary. This is that, long range strategic goals. Who are we? What do we do? You have been provided the requirements. So we do a lot of capability driven design, but we must understand that a design must be verified to be compliant to requirements. The integrated master plan is the timeline. It's the schedule. We understand where are we going as we traverse along this path. When we talk about who is in the program, that's the organizational breakdown structure. And when we talk about decomposing who's in the program versus what that person with that role needs to do, that is the work breakdown structure, where we say these are the products that happen from point A to point Z in our life cycle. These are the maturation statuses that those products have. This is how we relate the product maturation statuses to review. And then we can say, okay, by this review, this product needs to be at this maturation status for this team. Yay. We continue on down that path. The specifications, plans, and reports are things that show up as products in the work breakdown structure. So the culmination of this material represents the ConOps and OpsCon and more. But that is in general what you need. You can get away with doing 2 documents, ConOps and OpsCon, but we find it better to decompose this more specifically. All right. Questions, OpsCon, ConOps, how we decompose those in the work breakdown structure, product breakdown structure, integrated master plan. All right, moving on. So now we're going to talk about requirements. Requirements-driven design is generally, unless you're in a big program, a disaster. A lot of people do capability-driven design. This is going to help us understand what are good requirements. There are good requirements, there's bad ones. So stakeholders are going to say, I want this. I want a fast horse. I want a warm seat, that kind of thing. That's documented in that ConOps. So use cases can say, what do we need to do with the system? And then generally you will define the output, work your way backwards, and then understanding what you need to output and what you need to input, you can get a use case out of that. Or a behavior, a use case has to have something invoked out of it. For physical architectural actions, you understand what box this should fit in, what does it need to mate to. Your interfaces are always going to be matter, data, physical, or energy. They can always be described in terms of those 4. So again, your complex system has lots of interfaces. Your complicated system has lots of inputs and outputs. These can all result in requirements. Here's a visualization from Wasson about where requirements come from. So again, we're going to start with the I want statements, the stakeholder needs and capabilities in that voice of the customer, which is I want this. Then you can get to stakeholder requirements, where we start to understand what is a stakeholder requiring of us truly? I want a faster horse. I want to move faster. You are not getting to the actual system requirement. You are just getting a little bit closer than I want a faster horse. Then, once you understand your stakeholder requirements, what they truly want in their desires, then you can start designing a system that is validated. It's the right thing for their needs. And then you start decomposing that. You might have a single system, or you might have a system of systems. If you can generally go from system, subsystem, component, or assembly, subassembly, component. There's a variety of ways to do it. But as you get lower down into the weeds of what you're doing, that's when you start talking about specifications. Okay, so generally, if you're talking about a system, that's considered a requirement. But if you're saying I need this component to do this to this level of performance, that's going to be a specification. You will also hear the term specification in terms of an organization of requirements. So a specification is a low-level requirement, and it is also a set of requirements and information about requirements. They're used a little bit interchangeably here. We're going to talk about three types of requirements: functional, performance, and non-functional. So functions are unitless. Functions either do or do not. There is no try. This is something where if something needs to lock or unlock, it's going to latch or unlatch. That is just what happens. It does that thing. Performance requirements is where you add a level of performance to the function to get a capability. And this is often likened to a vector. So if a vector has a direction and a magnitude, a capability has that function and a level of performance. Functions are unitless. Capabilities have a level of performance prescribed to that function. Non-functional is, I'm going to do this with respect to this regulation. I am going to file this report at this date. This is not a functional requirement. It's not a capability. It's just something you're going to do, but it is not something you would need to do with the system. So remember, the specifications is as you get into the weeds, that's where they live. And here are a couple of categories or types of those. I won't step through all of these here, but some big ones that you are frequently going to see are capability requirements. That's the one where you're saying, I want this component to do this to this level of performance. Constraint requirements is where you're going to see this structure needs to be built to these tolerances. That's a constraint requirement. Interface requirements, this component is going to speak in an RS over an RS-422 communication, or maybe that connector is a micro D 15-pin connector. So those are just examples of the types of lower level specifications. But you can notice that in none of those, none of them were for the system. It was for all lower level components. Cool. There's a good way and a bad way to write these requirements. Requirements are always written who shall what. And even as you go down the different levels, system, subsystem, assembly, subassembly, whatever, you're going to want to say the system shall, or the subsystem shall, or the component shall. Who shall what? So organize your requirements according to the level that you care about. You do not want to say the system shall unlock this little tiny thing at this very little tiny level of performance. You want to relate what you're doing to the level that matters for when and where you're doing it. So there's all these different parts: source, verb, outcome, relational operators, maybe if you have them, level of performance if you have them. So this is, you have an ID. That is just one way that we've set that up. The GNC subsystem shall have attitude sensors capable of determining the spacecraft attitude. That is the outcome within 1 degree. So within is that relational operator, and level of performance is 1 degree. So if you have a level of performance and you have a function capable of determining the spacecraft attitude, you have a capability. So capability, function plus level of performance, you see the word capable in there. That's intentional. So good way and a bad way to write these requirements. The way we speak about these things matters. Here are some examples of the statements. Function, so we shall localize its relative attitude on orbit. Cool. No level of performance. It either does or it doesn't. Performance is we have attitude sensors. That's that same one. Non-functional is we'll submit an end of mission plan to NASA consistent with NPR 8715.6 and standard 8719.14. Non-function, it's not a performance. Non-function performance or requirement statement. Yay. Questions on requirements. Pushing on through. Everybody good? All right, moving on. Integration is the hardest part of systems engineering. It does not get more difficult than this, but it also is the most fun. So let's jump in. Assembly and integration are not the same thing. Assembly is putting stuff together like fabrication. This is, little parts. You're just putting it together like Legos, but they're all the same type of Legos. You're not putting a Lego dinosaur with a Lego Star Wars set. It's going to be the same type. You are assembling it. You are not integrating Star Wars fan art with Jurassic Park. So subsystems can be assembled individually. You can integrate subsystems, but they are generally more complicated subsystems. Integration is when you have components with lesser complexity being combined to form systems of greater complexity. And there's a question of, well, how do you measure complexity? That's not an easy thing to answer in the amount of time that we have today. But a way that I want you to think about it is in terms of emergent behavior. If you have components that have lesser complexity and they do use cases and behaviors individually, and then you put those things together and you get behaviors and use cases that did not exist with the individual components, you are probably doing integration. So that's not a strict requirement, but emergent behaviors is a decent way to think about it. All right. So with assembly, you got to understand where the material came from. You're going to need to procure it with enough time, 12-week lead time before you're going to get certain components. Oftentimes when you're assembling and integrating things, you realize that a problem with your drafts exists and you need to update your structural tolerances. Also, people drop things. There's breakage, electrostatic discharge. So arcs can burn out a component, release the magic smoke. You got to know how to assemble this, and there's entire NASA standards dedicated just to assembly. Integration, the problem is more that people tend to see things from their own point of view. So if you have a mechanical engineering degree, you're going to look at it in terms of the physical structure. You're going to look at it in terms of, how heat is influencing with it. If you're talking about software, you're going to see, well, how do I control this system? If you're talking about electrical, well, what's the cabling route? How is the computer controlling everything, not just how the software is written. So people tend to see things from a single point of view. And there's a really funny image that I should put on here where, a person who works on GNC will see the rocket as a big gyroscope. People will see what their discipline does. With software, it does become a little bit more difficult because software and EPS represent the vast majority of failures on orbit. Things fail due to software and electrical problems more so than any other. So those tend to get a little bit more attention, specifically because there's been some big name failures because of those. And we'll talk about that here in a second. This is one of my favorite stories. And it is about two watchmakers. They each are making watches out of 1,000 pieces. Tempus is making those watches from scratch. So he's putting all 1,000 pieces together. Aura assembles a subassembly of 10 components, and each component is made of 10 pieces. So Aura will put 10 pieces together, and then we'll make that component. And then they'll do that 10 times, and then they'll put a subassembly together, and eventually 10 times 10 times 10, they have 1,000. If there's a 1% chance that both of them are interrupted and they have to start over, it will take Tempest 4,000 times longer to assemble a watch than it will take Aura. The lesson here is that in order to integrate a complex system like a watch, you'll do it much faster if you have stable intermediate forms. So I hope all of you are hearing that in your development integration plans and qualification plans, we're asking you to communicate what are your stable intermediate forms when you're putting things together, so that we can define the behaviors and the use cases for those stable intermediate forms. And then we can start testing integration tests, which we'll talk about in a second, for those stable intermediate forms. We move fast, we don't break things, make $1 billion. This is what that looks like graphically depicted. So drawings go from left to right. You draw the entire system architecture first, start with your output, work backwards. And then finally, as you understand the components required to meet the needs of your system a little bit better, then you start to integrate those from right to left here. So everybody's integration diagrams in their development and integration plans is just one of these kind of jellyfish looking diagrams. You understand what the components are, and then you put them all together, and then they become part of a larger system. So this FireSat, which was created by Jerry Sellers, representing the Space Mission Analysis and Design, also known as Space Mission Engineering, big red heavy textbook. This is a good example that's been used in a lot of places, a lot of different ways. This is what it looks like to graphically depict that. We are doing this in SysML, but we are working with y'all to understand what your stable intermediate forms are. Okay. There's some general guidance that should help everybody do this successfully. You want to determine what your critical system parameters are, and that is generally technical performance, which there's a section on here in a little bit. So if you have a hard time allocating a requirement to a subsystem, that is a good indication that that component is going to be difficult to integrate. It's going to be difficult to get your behaviors and use cases out of that integrated configuration item. So then you identify the chains that you're putting together for stable intermediate forms that result in those critical parameters or technical performance measures. So that chain is an integration chain. I'm going to put this together, and then this together, and then this together, and then this together. Then finally, you integrate the configuration items, which happen at integration points, along those chains of subsystems. So if you define your configuration items, you have your integration points. It's confusing. This is what we said. Integration is the hardest part of all of this. What are your technical performance measures? Identify the chains that result in those technical performance measures, integrate to realize those systems. So that single integration point can be the result of many integration chains. So if you have 3 chains, maybe an electrical, avionics, and structural, those might result in a single integration point. This is what it looks like graphically. You're going to have to involve both technical and systems engineers to do this correctly. I want to pause here for a second. Questions, integration points, configuration items. What's the order that we do this? Identifying technical performance measures, which we'll talk about in a little bit. Everybody good? All right, moving on. This is for software in particular. There's this in the loop nomenclature, XIL. You have model, software, processor, and hardware. Software people, you probably are catching on to this real quick. Model in the loop, there's no actual hardware. This is development software. For software in the loop, you understand that your development software gets a little bit more mature, and you can start messing around with some simulated processors. For processor in the loop, you put your real-time controller, whatever controller you're planning on flying, put your production code on that and then start testing it, but you're still going to simulate the environment, maybe simulate some of your sensors. And then hardware in the loop, you have your production controller, you have the production software, and you have the production sensors, and maybe you simulate your environment. This is a table that represents that. So model in the loop, everything is simulated, you're developing the code. Software in the loop, code still in development. You might use a Raspberry Pi to put that code on. You're still simulating the sensors in the environment. Processor in the loop, codes production, controller production, you're still simulating everything. So processor in the loop is really just going from a Raspberry Pi to a more expensive computer. And then hardware in the loop, everything is production except for the environment. Then you're ready for TRL6 testing, because or TRL5 as well, because this is still TRL4, technology readiness level 4 lab environment materials. Okay, so if you're James Webb, if you're the biggest, baddest, most expensive piece of hardware that humans have ever put together, you're not going to skip any tests. You're not going to skip a single thing. And that's why James Webb took so long and they spent so much money on it. But if you're a satellite program, a CubeSat at a university, yeah, you could probably afford to skip some stuff. You don't have a $1 trillion budget. You're not going to be able to do everything because you don't have the resources for everything. So how much is enough? Where do we draw the line at how much is too much? There are countless programs that says that the plug got pulled because they spent too long testing and they spent too much time and money. And so they said, no, I don't think we're seeing the value that we expected to. This is taking too long. And that's when they go to a stage gate review and they get a kill on that because they took too long. The program management was not effective and efficient. However, there's also the Ariane 5 and Mars Climate Orbiter. Those are stories of how they didn't test enough. They skipped too many steps and then things broke. Billions of dollars was lost. Ariane 5 was a stack overflow and a GNC component that the computer suddenly told the rocket it was upside down, and then it started to turn itself and then itself up. The Mars Climate Orbiter, I want to say it was Lockheed, but they were building a navigation component, and there wasn't a GNC person in the admin team of the Mars Climate Orbiter. And Lockheed Martin, I want to say it was, they output their units in freedom units. I want to say it was inches or something stupid like that. And the rest of the civilized world uses metric units. And so one was telling each other in inches, and I think the other one was in centimeters. And they kept propulsively correcting because they couldn't figure out why they weren't on target. And by the time they realized what the problem was, they were out of fuel and they crashed into Mars. So super stupid. There's a spectrum here. You can either get it canceled because you spent too much time and money, or you don't spend enough time and money and something fails or breaks and you don't win. You don't make $1 billion. So where's the happy medium? That's the balance that we have to strike. That's in particular why integration is so hard, as we understand that you should define your technical performance measures, understand the chains that result in those critical parameters, and then integrate along those chains. All right, integration. Any questions at all? Here for them if you got them. All right, chugging right along. V and V. This is the lifeblood of systems engineering that fuels the heart of champions. This is what we do best. This is, I mean, we are truly kick-ass at this one. So verification, did we do it right? Validation, did we do the right thing? Did we do the thing right? Did we do the right thing? Okay, so verification, this is we have to verify that the design is compliant to the requirements. That is requirement-driven design. You got to plan this early. This happens for all systems, and if you don't do this well, you're gonna end up in specify, design, build, test, fix. So how do we verify stuff? Validation is, did we do or did we do the right thing? Okay. If the cardinal sin in systems engineering is to do something exactly right for the wrong reason. You did something perfect and you spent a lot of time doing it, but it's not what you were supposed to do. So you've wasted time, you've wasted money, and we can't get that back. So you have to understand what your user wants. And by taking in the stakeholder needs, those I want statements, translating those into stakeholder requirements, and then translating stakeholder requirements into system requirements, and then decomposing those into components of the system, that's how we validate things. Now, it's a little bit more complicated. We're going to get into that here. For both method, verification and validation, there's 4 methods: analysis, test, inspection, and demonstration. Test is measured compliance. Demonstration, observed. Analysis, predicted. Inspection, documented. Okay, there's also similarity, which says, this is probably pretty close. We don't do that here, but that does happen sometimes. So you have to know what is the method, and for every requirement that gets written, you write the method of the requirement as well. You have to know the level, because you're not going to do the same type of verification for a system versus a subsystem or component. And you need to know the life cycle. We are not going to jump into massive costly testing in a qualification testing in pre-phase A. So it matters knowing what's the method, what's the level, when are we doing it? Cool. So this is inspection. We're going to start here. This is the documented compliance. You are reviewing drawings and data. This generally happens when you have received a certification of some kind from a component vendor. You understand, oh, this is the material that I think it is because it came with a certification that says it's that material. Cool. For analysis, this is modeling and simulation, where you build a model that has a modeling environment, and the execution of that model is a simulation. So when you do analysis when it is possible, when test is not feasible or is not cost effective, or verification by inspection doesn't quite cut it. You'll still test in case things are mission critical, like the system or people will die if you don't test this, or the cost of being wrong is too high per se. But if you can't do the test credibly, we'll get to analysis, and there's a flow chart we'll see in a second. Every analysis has 6 parts. There is not a single analysis that does not have these 6 parts. And if you are in a midterm or end of semester review, you have to show these parts. If you give a slide or multiple slides to each of these, you're going to do a phenomenal job, and make tables and stuff. Don't just do bullets. Problem definition: it is okay when you are trying to communicate concisely to boil it down to a problem statement. And it's imperative in that problem statement to not suggest what the solution is or the cause of the problem necessarily, sometimes, in that problem statement. So don't say any solutions, just what is the problem that we are experiencing. Parameters: what are your inputs? What are your outputs? What are your technical performance measures? What are your key performance parameters? We'll talk about that after this. Assumptions: is it steady state? Is there heat generation? Is there, what are my boundary conditions? What are we assuming is negligible? Those are assumptions here. Methodology: in our program, we use domain knowledge maps for visual representations of analysis methodology. They're documented in the subsystem analysis plan. Results, conclusions. Cool. So models themselves need verification as well. You can't just make a model and say, it's spitting out these pretty colors. I like that color. That must be right. You got to verify that the model itself is good. So NASA standard 7009 has a really nice framework for doing this. It's gonna it's Appendix E, where you'll see the criteria and it'll rank everything 1 through 4. So one of the number one things we ask people to look at early in the model is the data pedigree. Where is the data coming from? How much can we trust it? So if you rank your data pedigree 1, probably can't trust your data very well. If you rank your data pedigree 4, yeah, you probably have decent time. So this is a more formal way of saying garbage in, garbage out. Yay. For testing, there's 3 types, okay? And there's 3 categories as well. But with testing, you have development tests. Development tests are going to be for TRL 1 through 5, technology readiness level 1 through 5. We'll talk about TRL at the end. This is telling us what should the system design look like. You are testing in order to understand the definition from your architecture, the what, to the how, the design. Qualification is to understand how the system is going to operate in its intended environment, in the operational environment, specifically the bounds of that operational environment. What is the absolute worst case that this is going to experience? Is it going to survive in that? For satellites, that is launch. That's a pretty bad one for Vibe. And for LEO satellites, they'll be going through eclipse, so you'll get really hot and really cold. Plus vacuum kind of sucks. So you got to understand Vibe, TVAC for satellites. Yay. Acceptance tests. Acceptance tests are more about workmanship. Did this thing get fabricated the way that we wanted it to? Did the technician make any mistakes when they were making it? So this is proving it's manufactured, assembled, integrated correctly. But testing is more complicated and costly. So only test if you really need to. If you test everything, the plug is going to get pulled because you're over budget and over schedule. So the difference between verification and qualification is something that I didn't understand for a long time. There's formal definitions in the NASA Systems Engineering Handbook, but even then, I didn't get it at first. Verification is those 4 methods. Did I do the thing right? Analysis, inspection, demonstration, and test to show that you're meeting the requirements. And this is only done for really well-written requirements. And the verification by really low-level stuff, analysis, does not mean that something is qualified. Qualification is something that only can be done by test. You cannot qualify by analysis, because qualification is specifically determining, is the system going to work in its intended operational environment, the boundaries of where it could operate. What is the hottest? What is the coldest? What is the shakiest? What is the shockiest? What is my electromagnetic interference? What's the worst I'm ever going to get? It's performed once as long as the design doesn't change, which is why you do not want to go back and fix things. Because if you do qualification testing and it's good, and then you deploy it and something's wrong and you go back and change it, you have to re-qualify, or else it's probably going to break. That's where all the expensive stuff comes from. So these are the 3 categories of testing. The 3 types were development, qualification, and acceptance. Development testing is informing design. Qualification testing is informing its operation, the intended operational environment, and acceptance was determining workmanship. So these categories, functional testing is saying, does it work at all? Remember, function is unitless. This is not, does it work to intended level of performance? You could call that capability testing, but generally you could just say it's a function test with an associated level of performance. Integration tests, do the pieces work together as intended? Notice that and the next one, environmental, which says, does it work in the intended operational environment, includes the question, does it work? So an integration test and an environmental test is a functional test. Functional test is just more simple than integration and environmental. So integration is still in a lab. It is not an environmental test. An environmental test can be an integration test. You can decide to do both of those together, but you're running the risk that it won't work. It won't work because of the integration, or it won't work because of the environment, and you won't be able to tell immediately which one it is. So integration, mechanical, electrical, software, put it all together, do the pieces work together as intended. Environmental is going to be shaking it, baking it, shocking it, that kind of good stuff. What is the operational environment that I'm going to experience? Put it in there, see if it still survives after. If it lives, cool. But sometimes you'll test it to failure just to see where that limit is if you're unsure. So this is when you use that test, when analyzing it is not good enough. If the cost of being wrong is too high, if people could die if you get this wrong, you're going to test it always. Any critical system interface, which is mission safety, you're going to test that. You're not going to just inspect it to see, oh yeah, that's probably good. You at least want to interface test it for sure. Demonstration often happens during a test. You are demonstrating that something works because you're using it to prove that it works. So this is not to a level of performance. If you have, say, a hold and release mechanism holding your solar array down, you're going to demonstrate that it works. You're just going to release it. Yes, this does or does not work. Cool. So here's the flow. And this is probably the most important thing out of this whole section. How do we know which one to use? All right, let's walk through this. You got something, you need to know how you're going to verify its design is compliant to requirements. Okay, so you need, what is the data that I need to understand in order to verify the design is compliant to requirements? Okay, is that data given to us? Did the vendor supply it in a certification or something? If the answer is yes, then you're just inspecting. You're inspecting the data sheet. I need to know that the material has this modulus of elasticity or this electrical resistivity, and it has been tested by the vendor, and I have a certification that says here it is stamped. So if it turns out that that's wrong, they're liable legally. Certifications are legally binding. Okay. If you can't get the data from a certification, you can say, am I going to look at it? Can just looking at the system tell me what I want to know? Unless you're talking about like a solder mask or something on a PCB, that's generally not the case. Or saying that, we're going to have at least 2 deployment switches. Okay, we have 2. Cool. I looked at it. So no, let's say no. Looking at it does not do the trick. Can I use the thing to figure out what it is? If I can just, flick something open or take off an access port myself, yeah, I've used it, then it does work. And I've verified the design compliant to that requirement. If I can't use it, can I test? And it's not, can you test really? I mean, is it physically possible for you to do it? Because even if it's a requirement stating that you have some lunar radiation that's impacting a certain component, the component surviving, you can still test. It's just super expensive. So it's more, is it cost and schedule effective? Is it going to cost you an arm and a leg to test? Then unless it's mission critical or somebody's going to die if you don't, you probably shouldn't test. So if it's feasible and cost effective, sure, we go test, and we'll probably do, I don't know, 5-10 tests throughout the satellite development. And then finally, if nothing else works, that's when you analyze. Now, we in the ACSI, we do some analysis so that you can learn some of the principles and the equations involved in analyzing, but overall analysis should be your last version. And models or analyses evaluate technical performance measures. Analyses are performed in models. Models have a modeling environment, and modeling environments have users guides. All right. Any questions about verification and validation? Analysis, inspection, demonstration, test. All right, chugging right along. So now we're going to talk about technology readiness levels. This is the chart that you're going to see most often if you Google technology readiness level, and it is fine. It's fine. It's a little bit confusing here and there, and the confusing parts are in the use of target and relevant. Those two words don't they can be misconstrued in certain circumstances, but effectively you're going to start at 1 and you're going to go to 9. That's the plan. So 1 is going to be back of the napkin. 2 is I have thought about some analysis possibilities. TRL3 is generally when you have a proof of concept. TRL4 is you have tested in a lab or put it together, integration test, function test, anything. TRL5 is an environment test. Always. It is a development environment test. We'll have a table for this in a second. TRL6 is a qualification environment test. Remember, there are different types and categories of tests. Your types are going to be development, qualification, and acceptance, and your categories are going to be function, integration, and environment. Cool. TRL7 is you are demonstrating it in a space environment, and there's flight qualified. And 9, 8, and 7, they get a little bit wonky when you're talking about system versus subsystem. It is possible to get to TRL with TRL 8 without being in space. You don't have to do that. But if you look at TRL 7, it says demonstration of space environment. That's to say, this thing's fine. It's just confusing. So you can do TRLs for systems and subsystems and components. There's various levels. So if you have a bunch of subsystems that are TRL 6, but you haven't put that system together, that does not mean the system is TRL 6. That means the system, if it hasn't been put together, is TRL 2, because TRL 3 is where you get the proof of concept. So a big thing that I want to point out is, let's say that you have a bunch of components that you found that you want to put in space, and those components have already been to space, but they haven't been to space in the design that you're considering. You putting those parts that have already been to space, they're already TRL 9, in a new design does not mean that the technology readiness level is low. That technology readiness level of the design is TRL 9. When you still have to go through all the tests, but at that point, you're just making sure that the parts aren't going to fall off when you shake it in a rocket. You're just going through the technology readiness level steps. But if you're submitting a proposal, which some of you go to grad school and some of you will do this, if you're putting together a proposal and the parts have already flown and you just haven't put it together, you're not doing TRL advancement, you're doing design. Okay, so this is another breakdown of that 1 to 6 flow. If you have an idea, 1, model it all. 2, back of the napkin, model it all, for real. Proof of concept, something physical in hand. 3, this is different for software, and NASA standard 7123.1C appendix F, I think, has the TRLs. It's also in our systems engineering guidance document. 4 is you test it in the lab. 5 is development environmental tests. So you're putting it in a thermal vacuum chamber at like 10 to the minus 4 torr and at 0 degrees C or something. TRL 6 is qualification environmental test. So that's going to be 10 to the minus 5 torr, a deeper vacuum. You're testing it at minus 30 degrees C to plus 60 degrees C. That's a wide, it's a big temperature range, but you hear the difference between TRL 5, 0 degrees C, and TRL 6 is negative 30 to plus 60. TRL 6 qualification testing is defining the operation within the bounds, the absolute extremes of the system operation. Cool. So what we do for in-house components is a long march to TRL 6. We are getting to TRL 6, we are qualification testing, and then we're putting it in our satellite and flying it. That's the same for both payloads and for taxi in-house components. All right, here is that table for test types, test categories, and analysis. If it's TRL 1, this is low fidelity model. You've had any kind of inkling about a thing. TRL1. TRL2, that's going to be medium fidelity models. You have done something, but your data pedigree may not be great. You should probably go back through NASA Standard 7009 to update the verification and validation of your model itself. TRL3, you have a proof of concept. You don't necessarily have to have tested that system. You just have to have something in your hand. TRL4 is you got to test something in a lab environment. TRL5, development environmental tests. Notice that you cannot analyze yourself into TRL5. You have to test. TRL6, qualification environmental testing. You can skip TRL5 and go straight to TRL6. You're risking it for the biscuit, though, moving fast and breaking things, which some people do. All right. We talked about technology readiness. TRLs. Anything at all? Hadn't gotten a lot of questions. It's okay. All right. Technical performance measures. I'm going to call this the second hardest thing that we do. So we're going to start by looking at how NASA does this. And then we're going to talk about what TPMs are, what a good TPM for a system is. And then we're talking about what we do to represent it, to kind of round it off. So this is how NASA handles it. They have stakeholder requirements. I want faster horses. Great. Then they translate that into measures of effectiveness. Okay. Measures of effectiveness might be how fast you get from point A to point B, or your horsepower per se. Then those get translated into measures of performance, which might be how fast the hooves are moving and how much the horse weighs. I don't know. But you can see that this gets translated into a couple different things, but there's not a clear distinction between MOE and MOP. I find this confusing and stupid. But they do a couple of things well. You have a technical performance measure. I'm going to read this definition right quick. A set of performance measures that are monitored by comparing the current actual achievement of the parameters with the anticipated at the current time and on future dates. So effectively, you know what it is now, and there's a target value, and you're going to try and take what you have and get it to a target value. And NASA does a selection out of the measures of performance of TPMs. I find that very confusing, but it confirms their progress and deficiencies. Cool. Okay. You can have TPMs for individual components or subsystems, but if you have extremely important technical performance measures for your system, the entire system, mass margin, power margin, volume margin, link budget margin, those are key performance parameters. So this is the formal definition. Too much text on a slide. Try to fit it all in there. I'm going to read this. Those capabilities or characteristics considered most essential for a successful mission accomplishment. Major drivers of operational performance, supportability, interoperability. These are your big kahunas. These are the ones that matter more than every single other technical performance measure. And you can see at the bottom that out of all the TPMs, the KPPs represent a subset of those. So all key performance parameters are technical performance measures. All right, that's important. So this is a very important checklist. This is something, whenever you're figuring out, is it a TPM, you should ask, is it relevant for what I'm doing? And can I measure it? Okay, do I know the value, and am I expected to know the value better in the future? Do I have a target for the value, or something that I'm either trying to exceed or not trying to exceed? Okay, if I do exceed or don't exceed that value, what is the corrective action that I'm going to take to fix that problem? Can I trade cost, schedule, and performance with this value? Can I buy myself out of the problem in a way that the parameter is controllable? And finally, is it tailored for what you're doing? The best thing to do in systems engineering is what works for you within the supporting architecture of systems engineering theory. Okay, so we do not define measures of effectiveness and measures of performance. We just define knowledge points. And these knowledge points is anything that you need to understand a system's environment, behavior, structures, or operations that you can determine a value for. And there's two special kinds, and those are the regular kinds. The same stuff that NASA does: technical performance measures, key performance parameters. Cool. So all important parameters are knowledge points. They are things that we can evaluate, but not all knowledge points are technical performance measures. Okay, this is what that looks like graphically. So parameters exist. You have just this big sea of parameters that can exist. And then you have knowledge points, which are just some things that can be calculated about that. Okay. And then you have technical performance measures, which are very important knowledge points. And then key performance parameters, which are great for the entire system. Okay. So questions here, pausing for questions. No measures of effectiveness or measures of performance anywhere to be found. All right. So we use domain knowledge maps. We have a technical analysis domain. We've ontologically defined it. I don't want to go too much into ontologies here because we describe it in detail in the introduction to model-based systems engineering, which is another seminar. There is a domain ontology relationship map on the next slide, which kind of tells you how to understand what the concepts in a technical analysis domain are, and then how they relate to each other to form a domain knowledge map. What does this mean? Let's take a look. So looking at this chart, you're looking at a domain ontology relationship map for the technical analysis domain. So it's the same thing on the left as it is on the bottom. So you have scalar parameters, array parameters, matrix parameters, equations, modeling environments. So for example, a matrix parameter is varied by state. A source provides an equation. A modeling environment is comprised of modeling environment modules. A array parameter is an input to an equation. Okay, these are general. They are generalized. This is not specific. Okay, so the example that you would read here is scalar parameter is varied by state, but when you put that into a domain knowledge map, a visual representation of analysis methodology, you get, for example, solar emission heat flux is varied by thermal environment state. So it is extremely strict semantics about how these things can be related to each other. This map is the categories and the relationship between categories, and then you can apply your content to visualize analysis methodology. What does that look like? This is a domain knowledge map. It is read from left to right. So on the left, you have your sources. The source provides a parameter. Remember, the yellow was array parameter. We have on our subsystem analysis plane templates, we've added the legend. I'll update that next time. That parameter is an input to an equation. This equation calculates this parameter. This is varied by thermal environment state. Cool. And you can see the size of this right here, thermal environment state. This is an input to this equation, and then this calculates this knowledge point. So you see how this is an oval and the rest of this is kind of rectangular? That means that this is a knowledge point. Knowledge points here are ovals. This is just the convention that we have assigned here. So that means that this is also a knowledge point. So this has its own domain knowledge map. We are working to logically represent this on our incoming project management system so that this is all online and accessible to everybody for all of the different subsystems. Another example that includes models. So these 5, they're provided by ABEX's thermal control team. Then you have here, each of these has its own domain knowledge map because it is a knowledge point. Now, component thermal resistances are not technical performance measures. They're not things that we can we don't have a target value per se. It's just something that we are using and we can evaluate, but it can still be a knowledge point. So all of these are inputs into our Simulink thermal resistive network. So STRN, Stern, or Howard, as we like to call them, The Simulink is comprised of of Howard. The time series is an input to Howard, and Howard models the component boundary condition heat flux array. Cool. So these are just knowledge points that team has determined, and this is the visual representation of analysis methodology. All right, technical performance measures. Any questions? Had to ask. All right, move on. Last section before the summary. So risks are not consequences. A lot of times we see people say, well, the satellite could break this way, so that's a risk. Risks, they come from design decisions, but just because the launch vehicle has a lot of stresses or because space is radioactive, that's not a risk in and of itself. Risks are a consequence of the design, not general uncertainty. Okay. So you have to know what is the impact. You have to be able to quantify that in order for it to be a well-defined risk. So what about the design is quantifiable such that we can know what that impact is going to be? Okay. You can have subsystem risks that correlate to hardware or software. You can also have management risks if you don't have enough personnel allocated to a given topic, or somebody doesn't know enough at their job that they are not a liability, but they're not executing at the level you need them to. Or if one person knows too much in an organization, they're an information silo. That's a risk. But the consequence is not the risk. That's a design flaw. You need to get that person to share more information. So you can't have a risk for a design that hasn't been defined. You can't say, well, we don't know what the design's going to be, ergo that's a risk. No, it's not. Don't do that. Risk is a consequence of the design. The consequence is not the risk itself. Okay, so this is what a risk statement looks like, and the risk template has been provided to everybody here. It's in the Slack community channel. It's also available on the CubeSat Initiative website. So all of the risks are going to read the same way. So given that condition, there is a possibility of departure adversely impacting asset, which can result in consequence. Okay, let's do an example. Given that space is radioactive, there is a possibility of proton strikes adversely impacting patch heater power transistors, which can result in loss of heater power. Okay, loss of heater power is the consequence, but the consequence is not the risk itself. You can see that this is a function of our design. We have decided to use a power transistor to operate a heater. The proton strike can impact that heater, causing a single event effect like a single event gate rupture or single event dielectric rupture. And that can result in a loss of electric power to the heater. That's the consequence. So we'll rate this in terms of its severity, for the safety of the personnel or the safety of the satellite. It's one heater loss is probably not going to take the whole spacecraft down. For performance, yeah, it's going to completely break that one part. 5, sure. For cost, I might give this more than a 1, maybe a 2, because maybe you want to put a redundant power transistor in there. And then schedule, no, this is probably not going to cause a significant problem with schedule. You can have a likelihood there. The likelihood is for any of these. The performance times likelihood will be the criticality. Fine, we'll talk about what that does in a second. How are you going to handle it? What is the risk after handling it? That's just how this is the structure of the document's built. And then finally, it will auto-generate a 5x5 risk matrix for you. So all you have to do is put in the condition, impact, asset, and consequence. It writes a statement. You define the risk in terms of cost, schedule, performance, safety, and we've added regulation actually. If this is going to be a big problem for regulations, it'll make your 5x5. Consequences are not risks. A risk is a function of design uncertainty, not general uncertainty. Questions? Last slide in the section. You guys stuck it out this far.
I got
we
one
got
question.
one.
Yes,
Finally.
If you can go back to the risk template.
Certainly.
So
No.
So when we see like the numbers on severity, is there like a formalized process to decide those, or is that something that's like on the writers?
Yes, there is. In the risk template, we have explicit criteria for what it means to be 1 through 5. And it says that explicitly. So you do not need to say, oh, I think it's 2 or 3. You can go and say, oh, it falls under this category. It must be a 2.
Okay, thank you.
Our goal is not to make it easy for you to succeed. It's to make it hard for you to fail. That's you shouldn't have to figure that out on your own is the point. Appreciate the question. Anybody else?
I'd have a quick one.
Oh, 2 in a row.
It's along the same lines, but would that be the same for criticality? Like, is there like a scale?
Criticality, that is really that is going to auto calculate. It is just likelihood times severity. It's used in the calculation of where this goes.
I see.
Like 5 severity and 5 likelihood is going to end up here. 25.
Gotcha.
All right. Let's wrap it up. Okay. So we talked about who a systems engineer is, and I hope everyone here can understand that it doesn't matter if you're a software, electrical, mechanical, aerospace, doesn't matter. Every engineer is a systems engineer. It is just a matter of understanding systems engineering in the context of your domain, of your discipline. Okay. Every system has a life cycle. Some systems have multiple. That life cycle is usually defined by your domain, because you're not going to have one software that has a significantly different life cycle than another software. So domain is a good place to start there. Requirements are ultimately derived from stakeholders. You figure out their needs. I want faster horses. You translate those to stakeholder requirements. I want to go, I shall go faster. That's not a good one. But you translate the requirements, and then you translate it into system level requirements. And then you take those system level requirements, and then you break those down into subsystem or component requirements, and you finally get specifications at the very end. So you have to, the goal is for us to get to technology readiness level 6 by PDR. For all components that are not technology demonstrations, you have to be. That's for a NASA mission. TRL 1 to 5, analysis and development testing. TRL 5 to 6, qualification environmental testing. Always. That is the definition of those technology readiness levels. TRL 7 and 8, a little squirrely with their definitions. Go to, I think it's Appendix F of NPR 7123.1C. Integration's the hardest part. It doesn't get harder. The big things are to identify your technical performance measures, identify the components when you put them together that will realize those technical performance measures, and then integrate those along those chains to get to technical performance measures. Because what you can do is when you integrate lower level, lower complexity components to get a technical performance measure, you can then measure that technical performance measure and see if you did it right. That's kind of the point. If you can't measure it, it's not a technical performance measure. Cool. So you have identified something measurable, you put the thing together, and then you measure it. All right. Put that schedule together. Verification. Did I do the thing right? Validation. Did I do the right thing? The cardinal sin in systems engineering is doing something exactly right for the wrong reasons. You have wasted your time. You've wasted your customer's time. You have wasted probably a lot of effort and cheesecake, or I don't know what you guys like for dessert. Something along those lines. I eat when I'm stressed. That's where that comes from. technical performance measures have a target threshold. We are getting there, or we are trying to stay under that. We should be able to trade cost and schedule and performance for that. We should be able to throw money at the problem. If it is something calculable, but we can't control it, it's not a TPM. For us, in the Alabama CubeSat initiative, we do parameters, knowledge points, TPMs, key performance parameters. We used to teach measures of effectiveness and measures of performance, and students consistently were like, I don't get it. And I was like, you're right, this is weird. So we changed it. Domain knowledge maps are visual representations of analysis methodology that have strict semantics and syntax, where syntax means how an expression is structured and semantics defines what an expression means when it is structured that way. So you understand exactly a source provides a parameter. That parameter is an input to an equation. The equation calculates a parameter. Very simple, very easy, but you can't define a relationship outside of those is the point. This is covered a lot more in the model-based systems engineering seminar, which I probably eventually will redo. So citations, as we talked about. Thank you very much. I appreciate y'all just sticking this out and putting your best effort in. I hope this was educational. I hope that you learned something. And you know, appreciate you.
Quick question, Michael. So I know you said in the structural integrity chat that the first one I sent was good. I got a second one. Do you want me to analyze both of them, or just specifically go with what the first Colorado source sent me?
Oh, you're talking about hold release mechanisms? No,
Yes.
ultimately those should go in an analysis of alternatives so that we can characterize the problem space of we need multiple hold and release mechanisms in parallel. What is the architecture of those? What are their interfaces? What are the elements? Characterize the elements versus the domains, physical operation behavior requirements. We characterize the problem space against the solution space. That results in a well-created analysis of alternatives. We eventually then translate that into a design in the architecture and design specification.
All right, thank you.
Appreciate that. It was a good question. Anybody have any? Hey, thank y'all. I appreciate it. Did every engineer is a systems engineer? Did that land? Does anybody still disagree?
Not even a little.
Good.
I think you'd be shocked if I disagreed.
Yeah, you've heard this lecture like 5 times. Any more questions? All right, y'all. Always available. Hit me up on Slack. Y'all have a lovely night. Appreciate your time.
Thank you.
Thank you.
Thank you.